So hi there. Good evening to everyone. First and foremost, thank you very much for attending this introduction to ANSYS Mechanical webinar. My name is Anas. I am from Cybernet Systems Malaysia. So as you all know, today's webinar is going to be about the introduction to ANSYS Mechanical. Now, if you have any questions at any point of this webinar, feel free to drop them on the chat box and I will try to answer all of them at the end of this session. So here is the agenda for today. First, we are going to start with a little bit of introduction of Cybernet systems and followed by introduction of ANSYS. And then we are going through the introduction of ANSYS mechanical products that include a feature of ANSYS Workbench and Mechanical, and then a simulation type, simulation example of ANSYS Mechanical, and some additional options which associate with ANSYS and ANSYS Mechanical. And then we continue with coupling with ANSYS. And then I'm going to tell you a little bit about our services here in Cybernet Malaysia. And then we continue with demonstration. And then finally, we wrapped up with a Q&A session. So first, let's start with a little introduction to Cybernet systems. Established in 1985, Cybernet systems have been providing CAE solution and IT solution through product sales, contract analysis, consulting, and software development for over 30 years now. We have developed a partnership with more than 20 companies, mainly in the United States, including ANSYS, Synopsys, and Symantec. Now, the sales subsidiary of Cybernet System consists of Cybernet China, Cybernet Taiwan, Cyfan, which is based in Korea, and of course, Cybernet Systems Malaysia. Now, here, as you can see, Cybernet System has been working with numbers of group companies around the world for both sales and also development. Now, a little bit of introduction about Cybernet Systems Malaysia. Cybernet Systems Malaysia's office is in KL Eco City, which is located in Bangsar, and has been around for more than 1 year now. Cybernet Systems Malaysia was established in November 2018 as the fourth subsidiary in Asia, after China, Taiwan, and Korea. Now, our business here mainly revolves around CAE solutions, IoT and big data solutions, and also professional services. Our partners up until this point in time include ANSYS, Synopsys, and many others. Now, as you all know, Cybernet Systems provide all sorts of solutions. And those solutions are CAE solutions, and then visualization solutions, big data solutions, IoT solutions, IT solutions, and also engineering service. Now, for the CAE solutions, which is basically what I'm going to focus in on today, give total support of CAE utilization in various fields. Now, the main application areas include the mechanical systems, fluid systems, control system, optical system, and also electrical system. Now, an introduction of ANSYS as a simulation provider. Now, founded by John Swanson in 1970, ANSYS is a global public company based in Canonsburg, Pennsylvania. It develops and markets multi-physics engineering simulation software for product design, testing, and operation. Now, as you can see on the slide here, those multi-physics include almost every conceivable physics analysis you can think of, ranging from a simple structural analysis all the way to a system simulation. Now, for 50 years, ANSYS has been the class-leading multi-physics simulation software provider. Due to that very fact, ANSYS now has been used worldwide with over 45,000 global customers. Now, ANSYS is also used in a wide range of industries, including automotive industries, electric and electronics, aerospace, and many more. Now, as I said before, ANSYS provide multiple physics simulation for every type of needs. For example, as you can see right here on the slide, they provide mechanical solutions, fluid solutions, electronic solutions, solution for designers, which is basically a specialized for special designers. And then some additional option, which includes something like a parallel computing module, material data selection library, and so on. The one that we'll be focusing on today is the mechanical solution. Now, the analysis included under the mechanical solutions are static structural analysis, dynamic analysis, impact analysis, thermal analysis, fatigue, and so on and so forth. Now let's get into more details on mechanical solutions. Basically, there are three types of licenses of ANSYS Mechanical. Now, in simple terms, the licenses of these solutions are depending on the complexity of a certain need for analysis and simulations. Now, the highest license provides the most access to different type of analysis and simulations, while the entry-level license gives you enough access for the general purpose analysis. Now, the first one, the entry-level license is called ANSYS Mechanical Pro. It includes a full thermal analysis, and then model analysis, full contact, which include every type of contact in ANSYS Mechanical, and then also include nonlinear geometry, a little bit of nonlinear material as well, which is material plasticity. The next one is the ANSYS Mechanical Premium, which in additional on top of everything that I've just mentioned before, you can also have access to full linear dynamics analysis and also a feature called element birth and death. And then, of course, the top of the range license here is called ANSYS Mechanical Enterprise. Basically, ANSYS Mechanical Enterprise gives you access to everything that ANSYS Mechanical have to offer. For example, you have the full material nonlinearity that include something like hyperelastic and viscoelastic material. And then you have the couple field element and also user materials. Now, if you see on the right side of the slide here, there are an additional ANSYS products that is not included in the mechanical license. You can think of it like an additional solution for a certain specific problem or need. Now, the first one here is the ANSYS LS-DYNA. It is one of the explicit dynamic solutions that ANSYS provide. Now, LS-DYNA is one of the class-leading explicit dynamic solutions. It is great for drop tests or collision analysis or something like that. The next one here, we have the ANSYS AutoDyn. Now, like LS-DYNA, AutoDyn also provide explicit dynamic solutions. It is mainly used for advanced explosion and impact analysis. And then another additional solution is the ANSYS ENCODE Design Live. Now, this is for advanced fatigue analysis. Now, for those who want to take a step further in fatigue simulations, this one includes something like vibration fatigue, high temperature fatigue, and spot fatigue, so on and so forth. So now let's talk more about the ANSYS Workbench and how does it work. So actually, one of the main reasons that make ANSYS the class-leading simulation software is because of its easy-to-use simulation environment. It was done thanks to the introduction of ANSYS Workbench. Now, what is ANSYS Workbench, you might ask? Now, ANSYS Workbench is a platform for delivering a comprehensive and integrated simulation system. The platform is based around an innovative project schematic, which is view which ties together the entire simulation process. So basically, the users are guided through even complex multiphysics analysis with a drag and drop approach to select the modules and capabilities required for each simulation task. Now, using Workbench for your product development simulation will result in higher productivity from integrated application and access to multiphysics and also systems level capabilities. Now, for this part, I'm going to explain about the features of ANSYS Workbench Mechanical by explaining a sort of step-by-step procedure when you are doing an analysis with ANSYS. Now, the first one, let's start with the material model definitions. So basically, this is where the users define what kind of material that they wanted to use by using something that we call engineering data. Now, the engineering data is where the users model the materials for the analysis. The users can either define the material and its material properties manually, or the user can simply choose the material of interest from the engineering data sources, which is basically a library of materials that users can access to. Now, the engineering data also equipped with a curve fitting function, which is very useful for most of the material. Then we go to the next step, which is a CAD model import. Now, ANSYS have a feature called bidirectional CAD associativity. Now, what this means is basically any parameter change in the user's CAD software, ANSYS can automatically read and apply the change inside the analysis environment. Now, some of the CAD software that support bidirectional CAD associativity are something like CATIA V5, Autodesk Inventor, Solid Edge, and so on. Now, with the advantages of ANSYS to support many 3D CAD data formats, of course. General purpose formats such as IGES and also STEP file can be imported inside ANSYS as well. And one more neat feature of ANSYS is the automatic contact generation. Now, after the CAD data has been imported into ANSYS, the algorithm will read, detect, and generate automatically any relevant contact at any interface of your assembly model. Now, if the user is dealing with a complicated assembly, say for example, we're talking about hundreds of parts, this feature will help to save a lot of users' time. So next, we continue with the mesh generation of our model. Now, meshing is an integral part in the engineering simulation process. This is basically where complex geometries are divided into simple elements that can be used as a discrete local approximation of a larger domain. Now, ANSYS provides a general purpose, high performance automated intelligent meshing software, which produces the most appropriate mesh for accurate, efficient multi-physics solutions, ranging from easy automatic meshing to highly crafted mesh. Now, ANSYS meshing is compatible with various element types such as a beam and shell. And then various meshing methods of ANSYS also allow the users to be really specific and also flexible with the meshing. So the next step of our analysis usually will be the definition of boundary conditions. This is basically where the users define the loads, the fixed points, and other type of boundary conditions on the model. Now, based on what you are seeing on the screen right now, the loads can be defined either as constant value or, if the users want, as a function of time and also maybe a position. So the users can be really specific about where and how to apply the boundary conditions. Now, ANSYS also has the advantage of flexible selection operation via something that we call as the worksheet. Now, it allows the users to specify the boundary condition selection based on the coordinate range, area, volume values, and also the elements of your model. Now, ANSYS also have a data mapping function of which the users can import the boundary conditions data from external sources directly into ANSYS. And then finally, we go to the post-processing of our analysis. So this is where the users finally got the answers of basically all your hard work. Basically, this is where the result of which the users are interested in be displayed. In ANSYS, there are many ways the users can find and display the results. You can choose to display a contour diagram maybe a vector illustration, deformation, sectional view, and so much more. Plus, the great thing about ANSYS post-processing is that you can animate the deformation of your model as it took place. It is a very intuitive way to really understand what is going on in the analysis. If the users wanted to see the result at for example, a certain point of time, the users can check the tables and graphs output that has been generated automatically. Now, still on the subject of post-processing, ANSYS has a feature to export the results file as a text file or with ANSYS Result Viewer. Now, this feature allows the users to easily share the results and data to anyone without having to deal with a large file. Now, finally, there is also a report function included in ANSYS. Now, what it does is that ANSYS will read your whole analysis and then extracting every bit of important information, and finally compile and summarize all of those data into a report. Now, all of these features are really convenient when you have to share your analysis with someone else. So you can see the previews of some of the features I mentioned just now in the current slide. So next, let's take a look at the type of simulation available in ANSYS Mechanical. So here, as you can see, we have a linear structural analysis and also non-linear structural analysis. Now, for the linear structural analysis, it is basically the analysis for stress, displacement, safety factor, so on and so forth, when a certain amount of load is applied to it. So we consider these loads, for example, something as pressure or force or maybe displacement. As for the nonlinear structural analysis, this analysis takes into account the nonlinearity of the problem. So analysis that has the nonlinearity such as geometric nonlinearity, nonlinear contact, or nonlinear material can be done in ANSYS Mechanical because ANSYS Mechanical allows the users to do a nonlinear structural analysis. So next, we take a look into a buckling analysis. Like the structural analysis, we can do both linear and nonlinear buckling analysis here on ANSYS. So for the linear buckling, only small deformation with no x-axis and sudden contact can be considered as linear buckling. For example, an aluminum can subjected to a small top loading. And then for the nonlinear buckling analysis, this is basically when you consider the nonlinearity that I mentioned in the previous slide, the nonlinear geometry, contact, and also material. Then next, we take a look into the linear dynamic analysis or vibration analysis of ANSYS. The first one here is called model analysis. This analysis is to determine the natural frequency and also mode shape of your model or your structure. And then we also have a frequency response analysis or harmonic analysis, as you might call it. So this analysis is to determine the steady state vibration response of a model or a structure to a harmonic load. Essentially, this simulation is to study the vibration of a structure when a harmonic excitation is subjected to it. So we still with vibration analysis. Next, we have the random vibration analysis and also a response spectrum analysis. For the random vibration analysis, this is basically an analysis for structural response to random vibration loads. This type of analysis is used in case when the input is non-deterministic. And then next we have the response spectrum analysis. This analysis is for structural response to a transient excitation condition containing many frequencies components, such as earthquakes and waves. And the response spectrum analysis is almost similar to random vibration analysis, but its input is defined instead of being random or non-deterministic. So next we continue with motion analysis and also rotodynamic analysis. Now, for motion analysis, by using a module called rigid body dynamics, this analysis is done to obtain the motion characteristic of the assembly model. So essentially, this is the ANSYS version of kinematic analysis. Now, ANSYS has a feature to allow the users to study the structural behavior of the assembly model as well. Now, as for rotodynamics analysis, this analysis was usually done to predict a potential hazard of a rotating body due to a rotational speed. It is commonly used to analyze the behavior of structures, ranging from jet engine and steam turbines to auto engines all the way to computer disk storage. So continuing on the theme of dynamic analysis, we have the explicit dynamic analysis. Now, before we go into the product description and example, let me explain briefly about the difference between implicit and also explicit dynamics. Now, implicit and explicit refer to two types of time integration method used to perform dynamic simulation. Now, implicit method usually used when the problem time magnitude is relatively large, for example, 10 seconds to 1 second. While explicit method is used when the problem time magnitude is really small. We are talking about a few milliseconds and even microseconds. So explicit method is also used when the nonlinearity of the simulation is high. So there are three products within ANSYS that can be used for explicit dynamic analysis. The first one here is called ANSYS LS-DYNA. Like I mentioned before, it is a class-leading solver for explicit dynamic analysis. Now, ANSYS LS-DYNA is the most commonly used explicit simulation program. It is capable of simulating the response of materials to short periods of severe loading. Example of explicit dynamic analysis featuring ANSYS LS-DYNA is a drop test of a smartphone. And then next we have the ANSYS AutoDyne. Now, AutoDyne is an explicit solver specializing in high-speed and ultra-high-speed strain rates problems. Now, it is usually used in military for multiple applications. Some of those applications are high-speed ballistics, explosions, so on and so forth. And then next, finally, we have ANSYS explicit dynamics. You can understand this as ANSYS own explicit dynamic solutions. Now, ANSYS explicit dynamics explicit solver is based on AutoDyne. Therefore, the solving capabilities is basically the same between these two. Additionally, while LS-DYNA and AutoDyne need this additional license, ANSYS explicit dynamic is included with the mechanical enterprise license. So now we've done with the dynamic analysis. Let's take a look at thermal analysis of ANSYS. Now here we have the steady state thermal analysis and also we have the transient thermal analysis. Steady state thermal analysis is basically an analysis to find the steady state temperature distribution and also heat flux. This analysis supports linear and also non-linear thermal analysis problem. And then next we have the transient thermal analysis, which is basically an analysis where the temperature changes within time, with time. This type of analysis also consider the thermal radiation as well. So next we have the fatigue analysis. Now this analysis evaluates life, damage, and safety factor using the relationship between stress or strain and life of the model. So it includes multiple ways of approaching the fatigue analysis, such as high cycle fatigue, low cycle fatigue, vibrational fatigue, welding fatigue, high temperature fatigue, fracture mechanics, so on and so forth. Now, mind you that some of the fatigue analysis does need an additional product, the one that I've mentioned before, which is the ENCODE design light. So next we have the acoustic analysis in ANSYS. This type of analysis is used to investigate sound wave propagation in closed or open spaces. The user can express various wave phenomena such as reflection, diffraction, and interference, and can be studied intuitively. So next we have coupling analysis of ANSYS. I mentioned about ANSYS coupling capability several times before. Here we have several more of that kind of analysis. Now the first one, as you can see here, is the thermal stress analysis. The thermal stress analysis is done by applying temperature distribution obtained by the thermal analysis as the load condition for the structural analysis. This essentially means that the temperature from the thermal load was obtained from the thermal analysis and then applied to the structural analysis as a load condition. So in order to find the stress due to temperature. And next we have acoustic structural analysis. This analysis combines the acoustic analysis and the structural analysis. This type of analysis can be divided into two parts. A strongly coupled analysis and also a weakly coupled analysis. So next we have yet more coupling analysis. This one is the current thermal analysis and also a piezoelectric analysis. The first one here is the current thermal analysis. Now this is an analysis that simultaneously calculates heat generated by the current flow in a conductor and then the resulting heat conduction in that conductor. So this basically means that the thermal property of the model is analyzed by taking the current flow from the current analysis as the load condition, basically similar to the previous coupling analysis that I've mentioned just now. And then next we have the piezoelectric analysis. Now this is an analysis for modeling a piezoelectric body and obtaining the deformation state and vibration characteristic due to the voltage difference generated at the electrodes. Now similar to the current thermal analysis, this type of analysis takes the voltage differences as the load condition and applying it to the structure or body to see the deformation and vibration of said body. So now let's dive into the world of optimization. Design Explorer is basically a tool for engineers to do a parametric study. Now, not only that, this tool is also contains some feature that optimize not only the way you choose your parameter, but also optimize the end result of your study. So here are some of the analyses that can help you do exactly that. The first one here, as you can see, is the parameter correlation analysis. It analyzes the effect of parameters on the result and obtain the correlation and sensitivity result. So next we have the optimization analysis. Here we have the analysis that proposes the optimal parameter candidates according to the goals and constraints. So basically it means that you can set your goals and constraints based on your need, and the optimal parameters candidate will be listed down. Then, of course, we also have the Six Sigma analysis with Design Explorer. So this is basically one of the optimization analysis using the Six Sigma principle. It investigates the effect of input parameter variation on the result that the user obtains. So still on the topic of optimization, but with different approach, here we have the topology optimization analysis. Now, by definition, topology optimization is a mathematical method that optimizes material layout within a given design space for a given set of loads, boundary conditions, and constraints. with the goal of maximizing the performance of the system. Now, this analysis uses the phase of a structure as a design variable, set goals such as weight and compliance, and derives an optimal solution based on constraint. Now, after the optimal shape has been found, it can be exported in STL format for design verification or for further uses. Now, in ANSYS, topology optimization can be used in combination with structural analysis, model analysis, and even thermal analysis. Plus, ANSYS topology optimization can also optimize a solid structure and change it into a lattice structure, which in the world we live in right now, where 3D printing is becoming more and more accessible, is a very useful feature indeed. We're already going through some of the type of analysis that can be done within ANSYS Workbench and Mechanical. Now let's take a look at some of the examples and applications that benefited from ANSYS Workbench Mechanical capability. First, here as you can see, we have the structural analysis of LCD touch panel, like the one that you have on your smartphone right now. This analysis was done to evaluate the stress generated when a liquid crystal panel is touched. So basically every tap and swipe input from the human hand create a pressure on the screen, subsequently to the liquid inside the screen itself. So how does it work? So basically the touch panel uses a viscoelastic material, one of the nonlinear material that is available inside ANSYS. Touch panel use viscoelastic material to take into account the effect of viscosity of the liquid crystal. So this makes it possible to evaluate the delay of the reaction when pressing the fingers. So next we have, we take a look into an application of manufacturing process. This is a structural nonlinear analysis of a pipe bending process. In this case, we would like to know the behavior of the pipe with certain material. We also want to know its deformation. We're interested in what kind of stress develop on the pipe and so on. Now, one of the other ANSYS feature is we can define the rotational condition of the clamp and band die using remote displacement function. Now, remote displacement function is essentially mean a displacement condition that used to guide the displacement of a face or edge of a structure from a remote point. So here we have a crack growth analysis, so based on fracture analysis. Now the crack growth is one of the failure analysis on ANSYS. So basically this analysis is to evaluate the crack propagation direction and also distance when the material breaks. Now, ANSYS Mechanical offers a broad range of fracture mechanics tools, including the intensity factors, J integral, and also energy release rate. By using the stress intensity factor or J integral and also Paris rule as the failure criterion, both crack growth analysis, static, and fatigue are supported. Plus, the efficiency of the calculation can be increased thanks to the automatic remeshing on the area around the crack leading edge. So next, we have the example of explicit dynamics. Here we have a PCB drop test or PCB collision test. This is an example of an analysis of which PCB is composed of an assembly model of electronics components. Was dropped and collide on a rigid concrete floor. Now, explicit dynamic analysis allows us to capture the very short moments before, during, and also after the impact. We also set a condition for the PCB substrate and the capacitor to separate when a certain force is applied to it. Because in ANSYS, it allows us to set such kind of conditions like contact conditions between parts. With ANSYS, it is possible to confirm that the contact surface is separated by the impact force at the time of rock collision. So now let me briefly explain about several additional products associated with ANSYS Workbench and also ANSYS Mechanical. The first one here is a tool for model creation and modification, also known as the ANSYS Space Claim. Now, the ANSYS Space Claim is a 3D direct modeler with an intuitive operating capability. The CAD software also have the advantage of two-way linkage via Workbench, which means that the interchange between setting up CAD and your analysis in Workbench will be seamless. Space Claim also have an enhanced model correction and simplification function. It essentially means that most of CAD defects can easily be repaired with Space Claim. Space Claim can also create enclosure and volume extraction for fluid analysis quite easily. And then it also have a function to do a mid surface to change your solid geometry into shell. Other feature that separates Space Claim to the other CAD software out there is that the ability to import and edit CAD data from most of major formats. For example, the likes of CATIA, Inventor, Parasolid, so on and so forth. And then here we have another additional options for ANSYS Mechanical and also ANSYS Workbench. Here in Cybernet, we also have our own tool, our own software to further enhance the capability of ANSYS. So here we have a multi-scale sim. Now, the multi-scale analysis, it is a multi-scale analysis tool that enables detailed simulation considering the characteristics of the composite materials. It is almost similar to the ANSYS material designer, but multi-scale sim can perform a numerical material test on composite to evaluate a macroscopic and isotropic material constant without having to carry out an actual physical material testing. Now, the main function of the multi-scale sim are micro model creation, which is basically the users can model their own microstructure. And then multi-scale sim also have the function to do a homogenization analysis. This is basically an analysis to determine the material properties from the microstructure that the user just defined. And then from there, you can also do a macro model analysis. A macro model analysis verify the material properties acquired from the homogenization analysis. And then finally, you can also do a localization analysis. Now, here users can study the microstructure behavior from the macro model analysis that the user just done just now. And then finally, before we go to the demonstration, let me explain briefly about our services here in Cybernet, Cybernet Systems Malaysia. Here in Cybernet, we provide support for CAE deployment, including implementation, planning, education, consultation on policies, automation, and so on. So basically, the processes include two steps of service, starting with startup support service, where the consulting and milestone creation are done, followed by a construction of simulation environment, so on and so forth. So the next step in this operation support service, which comprise of different kind of support during operation, such as daily support service, consulting, sample data creation, automation, customization, and so on. So I believe now is the time for demonstration. Now for today, I have three types of examples that I want to demonstrate, but I am just going to use the first example here, as you can see on the screen, as the one that I show the step-by-step procedure of doing an analysis in ANSYS Mechanical. Uh, for the next two example, I will just go through the results and basically how did I achieve that result. So for the first example is the linear structural analysis of a pipe clamp. This assembly model consisting of pipe, clamp, and also bolt. We want to evaluate the stress of loading from internal pressure while the pipe is bolted. So as you can see, the boundary condition will be bolt pretension with 200 Newton and then a 1 megapascal pressure inside the pipe and also some fixed point to keep everything in place. Now for the second example will be the thermal stress analysis. Now this is one of the coupling analysis that I've just mentioned on the previous slide. This analysis will couple the thermal analysis and also the stress analysis. Now for this one, we are going to use the ball grid array assembly model. Now, if you can see properly, this ball grid array assembly model is actually a quarter symmetrical model, which means that this model is actually symmetrical on this plane and also this plane. Now, why would we want to make the model to quarter symmetrical or maybe half symmetrical? It is because by cutting the model into half or quarter, we reduce the number of elements that we need in order to mesh it, and therefore reduce the overall analysis time, and therefore can save us a lot of simulation costs. So one of the function of ANSYS is that you can do such kind of thing during simulations. Now in this case, we want to evaluate the temperature distribution and also the thermal stress of the assembly when heat is applied. Like I mentioned before, the thermal structural combination analysis basically that combines a steady state thermal and also static structural analysis. And then finally, we also have a model analysis, which we are going to use a frames construction in this case. For this one, we have two different frames assembly. One is with slightly different frame shapes, and then we are going to compare the mode shape and also the natural frequency between those two different frames assembly. Note that the middle mass that we are going to use, instead of using an actual model of mass, we just put something that we call a point mass, 1 kilogram of point mass. This way we can, like I mentioned before, we can reduce the simulation time and also simulation cost. So now let's get to the demonstration. So first what I'm going to do is launch a workbench. I believe I already launched it. Oh, not yet. Here we have now, if you already have the questions at this point, you can freely write that question down in the chat box and I will answer them at the end of the session. So here we have something that I mentioned before, the ANSYS workbench. As you can see, the ANSYS workbench is predominantly consists of project schematics. This is where you can lay down all types of analysis that you wanted to do in one single project file. So on the left side here, we have the toolbox, which consists of the analysis system, which consists of the types of analysis that you can choose from. Now, in this case, we are going to do a static structural analysis. Therefore, what I am going to do, simply choose this one, static structural analysis, and then drop into the project schematic as such. So now we already created our analysis cell. We call it cell A with a static structure under here. You can also rename this one. Example, right? And then if you remember, I've mentioned before, the first step of the analysis will be the definition of the material. So how am I going to do that? Like I mentioned before, we are going to go to the engineering data right here, double click on it. And then you will open a tab here, which consists of whatever material that you want to use. Like I mentioned before, you can either create your own material, say for example steel. And then here you can insert any type of material properties that you want, for example density, and then maybe the isotropic elasticity. You can enter all of the material properties manually right here. Or you can go to the engineering data sources, which is basically a material library within ANSYS, and then simply choose whatever material that you wanted to use. So we have a lot of material to choose from in this case. But for this particular example, I'm just going to stick with the structural steel. Now, structural steel is defined by default. It is always going to be there. So I'm just going to use the structural steel for the material. Then for the next step, we are going to import a geometry inside our ANSYS environment. So how I'm going to do that is right click on this geometry cell right here and then go to the import geometry and then browse for the geometry that you want to choose. In this case, I'm going to select this one, pipe clamp. I already made the model before, therefore I'm just going to simply add it or import it into ANSYS. Now, as you can see right here, this green check mark right here, this indicates that the geometry is successfully being imported into ANSYS. And then next we are going to launch the ANSYS mechanical. How we are going to do that? Simply double click on model right here. And then it will start the mechanical, ANSYS mechanical. Okay, right now, as you can see, we have already successfully imported the geometry into our ANSYS environment. Now, as you can see, the first step that I would like to do is go to this geometry right here, expand it, and then check each of every one of our components. So the first one here, we have the pipe, and then also the clamp, and also the bolt. So everything is there. And then the next part is we want to assign the material for each of our parts right here. Now, because we are only going to use structural steel for all of our parts, so I'm just going to simply select all of this and then just select structural steel right here. And just like that, each of our components right here has already been defined by the material that we just assigned. So say, for example, you have another material that you choose from the material from the engineering data. It will show up here and you can just simply select it to assign to your each of your particular components. And then the next step will be to check on the connection between your components. So here you see under the connection tree, we have contacts. Now, if you expand the contact, you can check there's a two contact in this particular case. You click on it and then you can see which part is in contact with each other. So you see the view. Now, if you can see properly, the outside wall of the pipe is in contact with the inside part of the clamp. And then for the next contact, it's basically the bolt surface which in contact with the clamp as well. So this is what I call before. This is what I said before as a automatic contact generation. So ANSYS automatically read your assembly and then detect the contacts automatically. So if your assembly is as simple as this, it's okay to just let it be. But if you are dealing with a highly complicated assembly, it is worth checking the contact before you continue with your analysis. And then for the next step, like I mentioned before, is the meshing of our model. So like I mentioned before, you can mesh this as easy as right click on the mesh and then click generate mesh. So right now, as you can see, it's already generated a good enough mesh to run an analysis to. But if you are not satisfied with the mesh, you can simply add more setting or add more local control on it. For example, I want to adjust the sizing of the clamp. I right click on the mesh right here and then go to insets and go to sizing. On the geometry, I'm going to select the clamp right here. And then for example, I'm just going to change the element size into maybe 1.5 limited. And then you right click on this clamp right here and then generate mesh on selected body. So there you have it. As you can see, the mesh is already been refined. So there's one of the capability of ANSYS. You can really be specific of which you mesh your model. Maybe the more important part of your assembly need to be meshed more. You can do that by using the sizing control. And then the next step is to define the boundary condition of our assembly or of our model. To do so, we are going first to the analysis setting. And as you can see here, we have a step control. Now the step control basically allow the users to change the load step of which the load is happening. Say for example, in this particular case, I will have two types of loading. The first one is the bolt pretension, which a force coming from the bolt. And then the next load is coming from the pressure inside the pipe, which is come after we load the bolt. So there are two type of load steps. So to do so, we are going to the number of steps right here and then select 2, click enter. And there you have it. We already have two-step analysis. Then what I'm going to do next is insert bolt pretension. On the geometry, I'm just going to select this surface right here and hit apply. And then on this, the first step I'm going to load with a 200 Newton of load. For the second step, I'm going to lock it in place. So there you have it. We already defined our bolt pretension. Simple step. And then we are going to also include the pressure inside the pipe. So I right click here and then select pressure. And then on the geometry, I'm going to select the surface of the pipe, inside surface of the pipe. And then here, we are going to control which step that the pressure is coming from. For the first step, we are going to let it 0, and then the pressure is coming from the on the second step, which is 1 megapascal. Then, of course, we are also going to include the fixed point here on this hole right here. So we are just going to solve it by clicking solve right here on top of our screen in the ribbon. Now, the simulation time may vary depending on how many cores that you are running with, because ANSYS does support a parallel processing. Therefore, if you have more than one core in your processor, you can take advantage of the capabilities of parallel processing. And then next, for the post-processing, what I'm going to do is that, let's say I'm interested in the deformation. So I'm just right-click on this solution, insert, you can choose between what you want. Next one, I want to see the stress. And also I would like to see the stress again, but only for the clamp part right here. So on the geometry, I select clamp, then click apply. And then simply right click on the solution and click on the evaluate all results. So now you can see what happened. This is what I call, you can animate the results with the ANSYS post-processing. This way you can help you to understand what's going on even more. So in this case, you can see on the first step, the load is coming from the bolt pretension, and therefore this one is moving first, and then you see the pipe is slowly moving outward as the pressure coming into the pipe as well on the second step. Now this is an exaggeration animation because I can control if I want to see in true scale, I can select true scale, but then it is a little bit hard to visualize what's going on. So let's say I need 0.5, okay. And then of course you can also see the stress. On the left side here, we have the legend, which indicates the maximum and also the minimum stress across your assembly. Okay, as you can see, the maximum is 99 megapascal, which is happening, I believe, around here and around here as well. Then also we can evaluate the clamp and also animate it as well. Okay, so that is for the first example. There's basically like a step-by-step procedure of how you want to run or how you want to do an analysis in ANSYS Mechanical. Now for the next two example, I'm just going to get through it quickly because I've already shown the procedure. For the next two, the procedure will basically be the same. So first, let's take a look at the steady-state thermal and the static structural coupling analysis. So like I mentioned before, this is a coupling analysis. As you can see, we have a steady-state thermal on the left side and the static structural analysis on the right side, linked together by a series of connection right here. Now, how you want to get to this two analysis right here? For example, you drag this steady-state thermal analysis anywhere inside the project schematic. And then you also drag the static structural analysis and then drop it into the solution cell right here. And there you have it. You have a coupling analysis, simple as that. Now for this one, I'm just going to show you the results. Okay, so here we have the steady-state thermal coupled to the static structural analysis. The first step is, of course, we define the material on each of our geometry. And then you also check the connection. In this case, there's a lot of connection because there's a lot of part involved. And then for the boundary condition, we input the internal heat generation at the center of the chip right here. And then a heat flux on this part right here. And also convection on this surface right here. As the result, temperature result from that setup, we have something that looks like this. Expectedly, the maximum temperature is coming from this part right here, and then as it moves away from the internal heat generation source, getting cooler and cooler due to the convection and so on. Now, from this temperature, this temperature distribution right here, we want to use it as the boundary condition for the static structural analysis. So as you can see here in the imported load, we have the imported body temperature, which is used as the boundary condition or used as a load for the static structural analysis. We also include a bit of fixed support and also some frictionless support. Because this is a static structural analysis, we need to keep everything fixed. And then as the result, we have something that looks like this. So this stress is strictly coming from the temperature that was generated by this part right here, which we analyzed in the steady state thermal analysis just now. So as you can see, as expected again, most stress coming from here due to the very high temperature around this region. And then of course you can also view the result for the ball grid array right here. How does it how the stress distribution coming to this ball grid array. And then of course, like I mentioned before, you can also animate and see how the stress or the deformation took place. Okay, so that's for the second example. Now for the next example is the model analysis. Now, like I mentioned before, there's two types of geometry that we use, and then we are going to compare between those two. Now, remember, model analysis is to find the natural frequency and also the mode shape of the structure. So here we have the model frame A and also frame B. Now, if you can see properly, frame B does have slightly different shape with frame A in this region right here. You can see it is slightly taller in this part, this rate right here. And then we would have expected that the frame B will have more structural integrity because of the shape right here. Now, again, the setup is almost the same as the static structural analysis. Only this time we include the point mass in the middle, like I mentioned before. Instead of using an actual geometry as a mass, we simply use point mass to reduce the simulation time and also simulation cost. And then again, next step, we check on the connection and also the mesh. And then we put a little bit of fixed support at these four holes, these two here and these two here. And then for the analysis setting, the max mode that we want to find in this particular case is 6. But if you think that your model will have more important modes to find more than 6, then you can always adjust this number according to your engineering judgment. And then the result is as shown. This is the first mode shape, which has happened at around 61 Hertz. And then let's take a look at the frame A. So the first mode shape is happened at 51 Hertz. Therefore, we can conclude that for this particular sort of geometry, the frame B holds have a better structural integrity as proved by the natural frequency that happened that we find out from this model analysis. And then, of course, you can also animate to see the mode shape of our model. Then we can check on the second mode shape as well. This is happening at 141 Hertz. And then, of course, you can go through all of it up until 6 because we only got 6 in this particular case. Again, same thing. But based on the frequency, natural frequency generated right here, we can conclude that frame B is more stiffer or stronger than the frame A.